Fusion power. It's the dream, right? A star in a bottle, giving us almost limitless clean energy. But, there's a catch. There's this one colossal engineering puzzle we have to solve first. What in the world do you do with the exhaust from something that's 100 million degrees hot? I mean, it's like trying to build an exhaust pipe for the sun. So let's get into it.
So inside a tokamak, one of these fusion reactors, you've got powerful magnetic fields holding the superheated plasma in place. But eventually you have to vent the heat in particles. All that stuff gets channeled into an area called the diverter. And here's the problem. If that raw heat hits the wall directly, it's like focusing the surface of the sun onto a dime. The materials just can't take it. Honestly, solving this exhaust problem is one of the single biggest hurdles standing between us and a working fusion power plant.
So in this explainer, we're going to break down a really groundbreaking new way to tame this crazy exhaust. We'll look at the core problem, a clever new way of seeing it, the engineering it took to control it, and the very first successful tests. And then, of course, we'll talk about the limitations and what this all means for the future of fusion.
All right, let's focus on that exhaust pipe, the diverter. The whole challenge here is to cool the plasma down from millions of degrees to just a few, right in that tiny moment before it touches any physical surface.
The solution they've come up with is a process called detachment. What scientists do is they puff a tiny amount of neutral gas into the diverter. This gas creates a kind of, a cooling fog, a buffer zone that soaks up the plasma's energy and radiates it away safely before it can smash into the wall. So when the plasma is hot and hits the wall directly, we call that attached. But when this cooling fog is doing its job, we call it detached.
Now this is where it gets really interesting. It's a massive balancing act. This isn't just some on-off switch. If you don't have enough of this cooling fog, the diverter parts can still overheat and melt. But if you use too much gas, that cooling zone actually starts to creep too far back up toward the main reaction, and it starts to hurt the performance of the core plasma. It's a classic Goldilocks problem. It has to be just right.
For decades, the big problem has been, how do you precisely measure and control this sweet spot in real time? Well, this is where a team at the TCV Tokamak in Switzerland came up with a really brilliant idea. You see, trying to stick a thermometer into a tokamak diverter is, it's just incredibly difficult. So the team asked a different question. What if we don't actually need the exact temperature? What if we could just watch the edge of that cooling fog, kind of like a tide line on a beach, and just see it move up and down? If we can control that tide line's position, we can control the entire detachment process.
And this is exactly how they do it. In the TCV Tokamak, the plasma interacts with carbon tiles on the wall, and that makes the carbon atoms glow. It turns out this cooling fog has a really distinct edge, a front where the light from a specific carbon ion, it's called carbon-3, sharply drops off. They can measure the position of this front, and they call that variable L-pole. So here's the key takeaway. L-pole becomes a proxy, a stand-in for the entire state of detachment. If you can control L-pole, you can control the heat.
So how do you take a clever idea like that and turn it into a real working system? Well, the team went on a classic engineering journey. If you want to control something, first you have to see it, then you have to understand it, and only then can you actually build a controller for it. And here it is, the blueprint. It's a classic feedback loop. A camera is constantly measuring the current position of that emission front, LPO. A controller then compares that measurement to where they want it to be. If there's a difference, an error, it adjusts a gas puff valve. That changes the plasma, which moves the front, which the camera then sees, and the loop starts all over again. It's so simple in concept, but just incredibly hard to pull off inside a live fusion reactor.
So let's just break that blueprint down into 3 key steps. We're going to call them see it, understand it, and control it.
First up, see it. This is done with a really specialized high-speed camera system called MANTIS. It's got a filter on it so it only sees that specific 465 nanometer wavelength of light from the C3, and here's the crucial part. It can find that emission front directly from the raw camera image in real time. That speed is everything. It lets him skip all the slow, heavy calculations that would make a fast feedback loop totally impossible.
Okay, next, understand it. Before you can control the plasma, you have to know how it's going to react. So to figure this out, they basically poked it. They sent a specially designed wiggle, called a multi-sign signal, to the gas valve. And by watching how LE pull wiggled in response, they were able to map out the plasma's unique dynamic fingerprint. This gives them a map, called a frequency response function, that tells them exactly how the system responds to different pushes and pulls.
And finally, step 3, control it. Armed with that dynamic fingerprint, they designed what's called a proportional integral, or PI controller. The best way to think about it is like a really smart cruise control system in your car. It is constantly looking at the error. That's the difference between where L-pull is and where they want it to be, and it calculates the exact adjustments needed for the gas valve to make that error zero. They targeted a control speed, a bandwidth, of about 7 Hz, which is a nice sweet spot between reacting fast and staying stable.
So, the theory is sound. The hardware's all in place. The controller is designed and ready to go. The big question is, does it actually work in a real multi-million-degree plasma?
And here we go, the first proof. This test is in a standard low confinement or L-mode plasma. The blue line is the target position they commanded, just a smooth bump. The kind of noisy red line is the actual measured position of the emission front. And would you look at that? It follows the target almost perfectly. The system is actively controlling the location of that cooling front for the first time.
But what about tougher conditions? I mean, what about the kind of plasma that future power plants will actually run in? Well, this slide shows a test in high confinement, or H mode. H mode is way more turbulent. It has these regular instabilities called edge-localized modes, or ELMs, and even with all that chaos, you can see the controller successfully forces L-pull to follow this challenging staircase pattern. This proves the method is tough enough to handle the real deal.
Now, it's really important to be honest here. The tracking is not perfect. You can clearly see the real-time measurement is noisy. It's jumping all over the place because of those plasma instabilities like saw teeth and ELMs. The controller is constantly fighting against all these disturbances. So while it's an absolutely successful first demonstration, it's not a perfectly smooth ride, at least not yet.
And that brings us right to the current limitations of this technique, because understanding what it can't do yet is just as important as celebrating what it can.
The controller's performance is basically capped by a few key things. You have these big unpredictable events like ELMs that can just smack the front around faster than the controller can react. The plasma's own behavior can slowly drift over time, and of course you have fundamental limits coming from measurement noise and just how fast the camera can take pictures. These are the next big challenges for the engineers to solve.
So, let's zoom out. What is the real long-term meaning of this work for our quest for fusion energy?
Okay, so this experiment used the light from carbon because the TCV Tokamak has carbon walls, but future reactors like the big one, ITER, are going to have metal walls. They won't have carbon, but they will intentionally inject or seed other gases like nitrogen or neon for the specific purpose of creating that cooling radiation.
And this, right here, is the crucial takeaway. This experiment wasn't really about controlling carbon light. It was a proof of principle for a powerful method. The real breakthrough is the technique itself, using light as a proxy, learning the system's dynamics, and then building a robust controller. This exact same method can be adapted to watch for the light from nitrogen, or neon, or any other element. For the very first time, it gives physicists eyes and hands inside the machine to actively tailor the cooling, putting it exactly where it's needed most.
This is a fundamental step towards solving that massive exhaust challenge. We're moving from just trying to survive the heat to actively sculpting and controlling it. And it leaves you with a pretty cool thought, right? We just saw a machine get taught how to read and control the light from a tiny man-made star. What else becomes possible when you master a skill like that?